Hi, everyone. I wanted to compute a moment of inertia for a rod. In this case, it's going to be a rod. Maybe it'd be a uniform rod, like maybe the barrel of this thing spun about its center. Of course, this isn't uniform. This is rubber on this part and plastic over here. But you can imagine a pencil or anything like that. It's one of the typical easy integrals that you can pull off to calculate the moment of inertia. So I'm going to do that as a demonstration, and then I'll use the parallel axis theorem to show you how you can find it as if it's rotated instead of about its center, if I rotate it about the end. So I'll use that with the parallel axis theorem. I'll do another video later where I'll integrate it about its end and see that you get the same answer either way. So let me turn it on my document cam and we'll get started. So when you're doing these, generally speaking, your integral that you're calculating for the moment of inertia, at least in the physics world, the moment of inertia is equal to I, and it's integral of r squared dm. The thing is, as with all integrals, the differential mass element that I choose has to not vary very much at a particular distance r. So in other words, if I made it, a macroscopic dimension along the r direction, then I have to do some averaging process or something like that. So I got to choose wisely on my differential mass element. Also, with a differential mass element, you almost always need to convert it to a density times a volume, or a density times a surface area, or a density times a unit length. The constants we use for that are, normally says lambda. We normally say lambda is equal to dm over dl, or that's one of the, if it's a uniform body, this would be a constant. And in actuality, you just say dm is equal to lambda dl, and if it happened to be in the along the x-axis, the dl will become dx. But this would be a constant. If you had a uniform surface distribution as opposed to just one-dimensional, then you normally say sigma is equal to dm over dA. And finally, if you had a volume, you normally use rho is equal to dm dv. And again, if you're using single integrals, you're going to try to figure out a differential mass element that has only one variable to integrate, in the dA or the dv. So in this case, we have a rod, and we'll draw it in an axis in a coordinate system. So here's my x-axis, and here's my y-axis. And basically, I have a rod that goes from negative L over 2 to L over 2. So this is L over 2 here. This is negative L over 2 here. Its total mass is m, which means I'm going to use this as a one-dimensional object. That means its lambda is technically equal to the total mass divided by the total length. So that's the constant. I'll just leave it as lambda when I'm doing the integral, but in the end, I'll have to plug that back in. So what I'm going to do is, for my differential mass element, is I'm going to take a little slice that's going to be out at a distance x, and of course the thickness will be dx. So the thickness right there is dx. It's out at a distance x, and I wrote that really small. The distance is dx, and the width of it is dx, and the distance away is actually x. So what I'll say is I is equal to the integral of r squared dm, and dm, of course, is going to be lambda times dx. And the r, the distance away from the axis of rotation, which is this axis right here, is just plain x. So I'm going to write the integral of x squared lambda dx. And I'm going to integrate that from x equals L over negative L over 2 to L over 2. So as you can tell, the lambda can come out in front. I'll just get lambda times the integral of x squared dx from negative L over 2 to L over 2. That integrates nicely to lambda over 3 times x to the third, evaluated at negative L over 2 and L over 2. That becomes lambda over 3 times L over 2 cubed minus negative L over 2 cubed. Of course, that when you cube a 2, it's going to become an 8. And of course, when you cube the negative sign here, that's going to make it be negative, and then you have subtraction of a negative. So subtraction of a negative is equal to the sum of a positive. So I'm ended up going to have 1/8 L to the third power plus 1/8 L to the third power. So that'd be 2/8, which is 1/4. Or excuse me, 2/8, which is 1/4. Yes. So this is ultimately going to give me lambda over 3 times 1/4 L cubed. Remember, it was 2/8, but it now became 1/4, so that gives me 1/12. And now I put in my lambda, which is m over L. So I've gotten the 1/4 and the 1/3 taken care of. Now the lambda is taken care of, and now let's say times L cubed. And lo and behold, that's our answer. One of these L's will cancel out, and I get 1/12 mL squared. If you look that up in the table, you'll find that is the right answer. Now, let's say we actually wanted to integrate it as if this is the axis. So what if the axis is rotating along the end? That's the y-axis, and we're doing it that way. Well, the parallel axis theorem says the moment of inertia about any point a distance h away from the center of mass is just given by the moment of inertia about the center of mass plus m times that distance h squared. So according to this, I should be able to take my center of mass calculation, which is 1/12 mL squared, and add to it m. Now, if it's not at the center, then I've moved it a distance L over 2, so the h becomes L over 2. And you can see that since that's squared, that's going to be L squared over 4. So that's 1/4 plus 1/12. So I get m L squared times 1/12 plus 1/4. Okay, 1/4, of course, to make it into a 12, I have to multiply the top and bottom by 3. So it'd be 3/12 plus 1/12 would be 4/12. So ultimately, I just get 1/3 mL squared. So in conclusion, our moment of inertia for our rod, uniform rod, of course, about the center of mass is 1/12 mL squared. And rod, again, uniform rod, about the end should be 1/3 mL squared. That's it. So that clears some things up for you.